So one thing that I sort of forgot to do in the last video was what's an example of solving a system of equations with parameters. So here's a whole bunch of equations, and we want to come up with the solutions to this set of equations. So what we do is we create an augmented matrix. That's this. Note that the coefficients here, there should be a line here. No, there shouldn't be a line there. So the coefficients here in this column, these are the coefficients of x1. Next column is a coefficient of x2, etc. We can think of these generally, we can also think of these things as being vectors, v1, v2, v3, v4, it's a v, and that's a 3, v5, we have 5 vectors, and usually I call that w. So what the reduced Roy echelon form can do, and that's what this is it takes this system of equations and it turns it into this system of equations. And the nice thing about the reduced Roy echelon form is that it preserves the solutions. The solutions to this set of equations are the same as the solutions to this set of equations. So if I turn these back into equations, right, this is x1, x2, x3, x4. These are the coefficients of these variables, and this is the right-hand side. What do we have? Bring this over here. x1 plus 2x3 equals 1. So that's this row. And then I have x2 minus 3x3 equals minus 2. And then finally, I have x4 minus x5 minus 4x5 equals 1. Note that I have these two columns do not have any leading ones in them. So what I'm going to do is I'm going to solve for the coefficients x1, x2, and x4. x1 is 1 minus 2x3. x2 is minus 2 minus 3x3. And x4 is 1 minus, plus 4x5. And that should be a plus as well, because we're going to bring this over. It becomes great. So what I want my solutions to look like, because I want to write these things in vectors, as vectors, is I want x1, x2, x3, x4, x5. So my solutions will be x1 equals, x2 equals, x3 equals, x4 equals, and x5 equals. So we know x1 is 1 minus 2x3. x2 also depends on x3. So we'll assign a parameter t to x3, and we'll assign a different parameter, say s, to x5. And then what does that make x1? x1 is 1 minus 2t. x2 is minus 2 plus 3t. And then x4 is 1 plus 4s. So this is very similar to how we parameterize lines, except now we're parameterizing in 2 dimensions instead of just 1. And so I can rewrite this as vectors, x1, x2, x3, x4, x5 equals 1 minus 2t minus 2 plus 3t, t, 1 plus 4s, and s. Now I'll break that apart into 3 parts. One has just the numbers in it. So 1 minus 2, 0, 1, and 0. There's no constant in this row or this row. That's one vector. And then we'll do plus t. So all the t terms go here. I've got a minus 2 here, and a 3 and a 1. That's this term, and this term. And then no t's down here. Plus s. And I've got a 4s here and a 1 there and a bunch of zeros. So this set of equations up here has got a particular solution. And a homogeneous solution. And why I call that the homogeneous solution will become clear next week. But I am trying to point out that this is very similar to the structure that we see when we're talking about the solutions to differential equations.